Mic and speaker it is okay. So you will have to keep your laptop on. Yeah, good actually, sir. I met these students.
हेलो सुरभि, ज्वाइन करो।
Yes.
और किस नाम से किया ज्वाइन आपने? नहीं, आपने तो अभी तक तो नहीं ज्वाइन किया, ना ही आपका नाम को होस्ट में आया। जब मैं बात कर रही थी देशमुख सर से, आप सुन रहे थे? जब मैंने बात की है देशमुख सर से, आप सुन रहे थे बात अभी?
अरे ईयरफोन
आपने नहीं ज्वाइन किया?
लगा रहे हैं
शायद अनम्यूट है।
खाई है मैंने लेके, ये वाली मैंने खाई, ये आपकी पड़ी हुई कसी।
इतना जाऊन घर आपको उंच रस्ता है नाही का? आज प्रदीप सर नहीं है।
डॉक्टर नीलम, प्लीज म्यूट योरसेल्फ। नमस्कार कटक सर, नमस्कार।
How are you?
आई एम वेरी फाइन विद ऑल द ब्लेसिंग्स।
बिल्कुल ठीक हो?
बिल्कुल ठीक हूँ सर।
Good to know that.
थैंक यू सर, थैंक यू।
So I thought that I should join little early so that
It's good, sir. It's very good. I was just trying to post a YouTube link to you through mail, but it's good to see you here.
चलो।
That's good.
क्या हो गया था तुमको? Food poisoning?
Namaste. Can you hear me, Professor Ajay?
Dr. Halim,
Yes, I have. Yes, I can.
Yes. Good.
सर नमस्कार।
Wonderful
नमस्कार।
to have you in the meeting.
आपकी इतनी बुक्स पढ़ी ऑनर्स फिजिक्स में कि आपको देख के बहुत अच्छा लगा। ऐसा लग रहा था जैसे कुछ सेलिब्रिटी होता है ना, हाय अमिताभ बच्चन, चलो चलो चलो। My sister did engineering and she was in Sweden and when she called me I said नहीं घटक सर का लेक्चर चल रहा है, फिर रख फोन रख बाद में बात करेंगे। For generations and generations, really, Ajoy Ghatak is a name, really brand name. बहुत अच्छा लगा आपका टॉक, really.
अच्छा लगा टॉक?
बहुत अच्छा लगा सर। प्लीज डू कम टू KMV sometimes.
कहाँ पर है वो तुम?
जलंधर सर।
हमारा
जलंधर, हाँ।
जलंधर, हाँ जी।
सर हमारा इंस्टीट्यूट
कितने घंटे का ड्राइव है दिल्ली से?
It is all right. It's important that
अरे आप फोटो बताइए, हमने ले लगाई
seeks to join someone else.
Have you done a separate machine for this? That machine here.
Oh my God. iPhone का जुबान
क्लियरिटी सर जब वो कार कपड़ू मुकिया પછી આખો લુક બદલાઈ ગયો ફોટાનો આ પાણી આ
ये फाइल को जाती
Good evening, Professor Deshmukh. Namaste.
Say,
They are in the crowd.
Namaste.
good evening. How are you?
Mention,
Namaskar.
Namaste, Professor Aluwale ji. Namaste.
Namaste. Yeah. Namaste, sir.
See you, Professor
Professor Ghatak, sir.
Ahluwalia.
Namaskar, sir. Welcome.
Thank you.
Where is the book?
I'll get it.
Professor Ajay. Professor Ajay Ghatak.
Yes,
Can you hear me?
yes, I can.
So I'm sitting here in the Senate room of the RD University,
Acha.
Bangalore, and the students over here have brought out a book about scientists in India.
Acha.
Who is the chief editor of that book? One of you? It was but you have written the article.
written the articles.
I can't hear you properly. I can't hear you properly. देखिए मेरा वॉल्यूम कहाँ है, कैसे ये ठीक करेंगे? Just 1 second. Exit full screen. Let me see whether my volume is full or not. No, now it is full.
So this is a book. Let me have a look. Is a book here?
Maybe I can send the cover photo. You can share.
What is the full form of RV? RV University. What is the full form of RV?
Good question. This university has been set up by a trust, which is called as Rashtriya Vidyalaya Trust.
Acha, Rashtriya Vidyalaya.
And I always thought that the name of the university is Rashtriya Vidyalaya University, and RV is an abbreviation. But I learned that the university is registered only as RV University and not as Rashtriya Vidyalaya University.
Acha, acha.
So the full form of RV is just RV, essentially.
And I have also not heard AMOST. AMOST.
Yeah, CMOS stands for Center for Atomic, Molecular and Optical Sciences and Technology.
Oh.
So this is the center which we set up at Tirupati.
Yes.
Tirupati is the only town in India which has got an IIT as well as an ISER. Stage of this and the possibility of India working together. This center. I happen to be the convener and mentor for the center. It's nearing 6:30 and I'm quite ready. So whenever you ask me to begin the talk, I will. Sir? I think we have to ask Dr. Neetu. Yeah.
Actually, today the master of ceremony is Dr. Surbi, and he is unable to unmute herself. So I am trying hard that she may unmute herself. Otherwise, I will start the.
What was the name of the participant?
It's Dr. Surbi.
Maybe on the next page.
Dr. Surbi, are you listening to me? Let's.
Is she logged in by the same name?
Dr. Surbi is not able to unmute herself. Dr. Helene, could you please see what is a
Ma'am, she has some network issue. I think she's not in the meeting now. I'm calling
okay?
her to
Okay,
join.
okay. So let's proceed.
1 minute, just.
So, formally, a very good evening to all distinguished guests and attendees, and my very special greetings to Professor Deshmukh ji, whose presence graces us with immense honor and privilege. So, on the behalf of organizing committee, I extend a warm welcome to a true pioneer in the world of quantum science, with groundbreaking contribution that have redefined our understandings of quantum world. Professor Deshmukh ji stands as a beacon of innovation and discovery. Sir, am I right? So,
No, you're not.
this week-long observance transcends mere academic discourse. It embodies a voyage of discovery, innovation, and collaboration. It exemplifies the collective endeavor of scientific community to push the frontiers of knowledge and usher in the new era of quantum technologies and applications. So today we have a privilege of extending a very warm welcome to our Professor P.C. Deshmukh, a distinguished scholar and mentor in the domain of atomic, molecular, and optical sciences. His forthcoming publication, Quantum Mechanics, Formulation, Methodologies, and Application, is poised to be a seminal work that will undoubtedly enrich our understandings of quantum phenomena. With over 3 decades of teaching and research experience at esteemed institutions worldwide, including IIT Madras, IIT Mandi, and Georgia State University, Atlanta. Professor Deshmukh is a foremost authority in his domain. His dedication to guiding undergraduate and graduate students, along with the young colleagues, underscores his commitment to fostering the next generation of scientists and innovators. The international acclaim garnered by his research group contribution to relativistics many-body studies of attosecond dynamics in atomic photoionization processes stands as a testament to his scholarly prowess. Today, we are honored to invite Professor Deshmukh ji to share his insight into this quantum world. His expertise and eruditions are poised to enlighten and inspire us so as to embark on this voyage of exploration and discovery. So please join me in extending a warm welcome to Professor Deshmukh ji for his talk on complexities of quantum land. So I would like to add, जो एक तिजोरी होती है, सर वो तिजोरी है, और हमें उस तिजोरी में से खजाना निकालना है आज, जैसे सर की टॉक होगी. So, sir, I invite you for your address.
Thank you very much, Dr. Neetu. I will first, I don't understand God and divinity and all, so I'm not known to be praying. But if at all I were to pray, I would have to pray that you are forgiven for all the exaggerated interaction you provided. So, let me begin my talk. I assume that my audio is all right. I just have one request to the co-hosts. I sometimes get messages on my screen that somebody is trying to join and so on.
Audio is not very clear. Is it true for me or for everyone? I can hear you, but there is little.
Well, Dr. Neetu, am I audible? Let us ask you
audible,
participants.
but some slight echo is there.
Yes, some little, thoda sa.
Little echo is there.
Chaliye, doesn't matter. Thoda aista boliye.
I think coordinator should mute all the participants for clear.
Sorry to interrupt, sir. Deshmukh sir, your mic is muted. Please unmute it.
No,
Yeah, now it's okay.
In that room where you are sitting, all the mics should be muted. Then it is okay.
No, wait. Where is the screen? Where is my full screen?
Take one from there. Immediately. Yeah, now. We'll not listen from there.
Yeah.
Now it's fine.
Can you hear me now?
Yes, sir. Yes.
Yes, sir.
And it is better also, sir. Audio is better now.
Volume has already been done.
If you, they are speaking, you will not listen.
You want me to turn on the volume? No, he first said that the volume should be switched on.
I think it is better now, sir. Your voice is clear. So you can continue now.
Hello? Hello? Can you hear
Yes,
me?
sir. Yes, sir, you are audible.
Okay, so is the audio all right now?
Yes, sir.
Okay,
So go
good.
ahead.
So I think let me begin the talk then. So if you are all ready. So good evening, everybody. Delighted to be here for this grand celebration of the World Quantum Day. It has got a very interesting theme, Alice in Quantum Land. And I chose a topic which rhymes with the topic of this, with the theme. Why am I getting this black bar over there? Yeah. Okay. So as this is a week-long celebration, and today is the third or fourth day, I think, and we already had some excellent talks in this series. The World Quantum Day is celebrated on April 14th because the Planck's constant, or what is normally called as the Planck's constant, is begins with 4.14 in appropriate units. If it is written in Joule second, it is 663, and there aren't 63 days in the month of June. So the units electron volt second are more convenient to declare April 14th as the World Quantum Day. It is a quantum of action, which is this integral of the Lagrangian, time integral of the Lagrangian. That is what the action is. And we can, however, celebrate it in June if we use atomic units, because in atomic units, it would be 2 pi, which is almost 6.28. And we do have 28th of June. We can have another celebration for the World Quantum Day, if you like. Now, let me begin with this. If you look at the bottom of this slide, here is a report which I have copy pasted. I need a mouse pad or something. That's not. Yeah. Yeah, just one moment. Yeah. So if you look at the bottom of the screen here, you see a report from Physics World, and what I have on this slide is a quotation directly from this report. And it points out that although Max Planck is widely credited for the introduction of the quantum, history shows that this is probably not what he had in mind. And the origins of the quantum of action, it has got a much more complicated development in history. And this report goes on to say that the discovery of quantum theory should not be seen as a moment of insight in December 1900. It was actually on December 14th, which some people regard as the birth date of quantum mechanics, when Max Planck presented his revolutionary ideas. But he was not quite convinced that it was the right way to go, and he did not publish anything for many years on this, between 1901 and 1906. And this was after Einstein's work in 1905 on photoelectric effect. And as a matter of fact, Planck thought that his hypothesis was reasonable only in 1908, which was well after Einstein's introduction to the Einstein's explanation of the photoelectric effect. So the development of the meaning that we assign to the quantum of action has got a long history. It began with Planck, sure enough, but then it needed the work of Albert Einstein and also Satyendranath Bose, who took into account the statistical distribution of photons and the Bose-Einstein statistics, as we know. So I always recommend that what we call as Planck's constant should actually be called as Planck-Einstein-Bose constant. And in my book, I actually refer to it as the PEB constant. Now, this certainly marks a huge departure from classical physics. And I would like to comment here on what is classical, and to a certain extent, even quantum mechanics is now becoming classical. And let me explain what I mean by this. Classical is a term that we use in the context of something which has withstood the test of time, like classical literature, classical music, classical dance. It is something which has been appreciated for a long time. And when we talk about classical physics, we are typically talking about the laws of physics as have been developed by Newton, Lagrange, Hamilton, which have already withstood the test of time for a few hundred years already. But now, quantum mechanics is also 100 years old, so it's not exactly like yesterday. So in a certain sense, quantum mechanics is also beginning to become classical in that sense of the term. And it has truly withstood the test of time. There is not a single experiment conducted anywhere which is in contradiction with quantum mechanics. So it's a very powerful theory, but it very dramatically separates itself from classical physics. And classical physics depends on the description of the state of a system by position and momentum. And quantum mechanics recognizes the fact that these two are not simultaneously measurable. If you measure one, you lose information about the other. And the more accurately you measure one, the less accurately you know the other. And it is impossible to get accurate information about the two, which means that classical physics, as was developed by Newton, Lagrange, and Hamilton, it just cannot work. And if it doesn't work, you need a new theory. And this is the new theory, which we call as quantum mechanics. So the question in classical physics as well as quantum mechanics is essentially the same. How do you describe the state of a system? And how does the system evolve with time? And classical physics answers it by saying that the system is described by position and momentum, and its temporal development given by dq by dt and dp by dt, which are there in the Hamilton's equations, and Lagrange's and Newton's equations are completely equivalent to that. They give you information about how the system evolves with time. Quantum mechanics appreciates that since position and momentum are not simultaneously measurable, you need a new mechanism. you need a completely new mechanism. And this new mechanism can be introduced in a variety of ways. And there are two alternative formalisms of quantum mechanics. And these two are popular formalisms. This is the wave mechanics developed on the principles of de Broglie and Schrödinger, in which the fundamental idea is that a system which has possible access to what in classical physics are considered as exclusive pathways must actually be in a state of superposition of these alternatives, which means that a cat must be regarded as being in a state of being dead or alive. It is a superposition of these two states. This is one way of introducing quantum mechanics. The alternative way, the first one, which is the de Broglie-Schrödinger way, is what we call as wave mechanics. And that it is in this formalism that you ask questions whether an electron is a wave or an electron is a particle. But in other formalisms, this vocabulary is not even relevant, because you can begin with this consideration that, okay, position and momentum are not simultaneously measurable. There is a basic fundamental uncertainty, and you develop matrix mechanics, develop operators, and so on. So that is the alternative formalism, which is matrix mechanics. Now you can have one cat which is in a state of superposition, but you can have another one. And then when both of these are in states which are in their individual states of superposition, but their combined state, you may be able to write as a product of their individual states, or it may not be possible to do so. And when it is not possible to do so, you regard them as entangled. And that is what is now behind what we call as the third or second quantum revolution. But then I must point out that there are not just these two formalisms of quantum theory. There is another one, which is the formalism due to Richard Feynman, which is the path integral approach to quantum mechanics. And I should go on to point out that there is a paper which actually refers to 9 different formalisms of quantum mechanics. They are equivalent to each other, mathematically equivalent to each other in a certain sense. Their conclusions are the same, but they don't necessarily begin with the question whether an electron is a wave or a particle. Their questions are different. They come to terms with the fact that classical physics doesn't work. You need a different theory. And they develop these different theories. And the one which is going to be most relevant to our discussion for today's seminar is Feynman's path integral approach, which is the third method which I mentioned here. And in fact, that is the one that I will be using quite significantly. So in all of these formalisms, there is a certain mathematical equivalence, but it is not 100%. There are certain things which one formalism explains better than the other and vice versa. So they are mostly equivalent, but not totally equivalent. But I will refer to the common platform in which they are mostly equivalent. And you have this state vector, which must represent the state of a system. So the first point of departure is this, that the physical state of a system is represented by a vector in the Hilbert space. Now we are into mathematics, and no harm in that, because nature can only be described in mathematical terms. There is no other way. We try to do it using our 5 senses or whatever tools we have at our disposal, and that is not appropriate to describe nature, and nature is not obliged to manifest herself in a manner which is convenient to us. Nature has her own expression, and it is our responsibility to develop an appropriate vocabulary, which it turns out cannot be in terms of position and momentum, or said in a different way, dog does not bark and bite at the same time, which is how I often state the uncertainty principle. So we will be using mostly Feynman's path integral approach in today's discussion. And let us remind ourselves that we come to terms that the system cannot be described in terms of position and momentum, but it is described by a state vector. And that state vector is this gamma, which is a certain label which describes that state vector. You get it from the eigenvalues of whatever operators commute, whatever measurements you can in fact carry out. And then how it evolves with time is given by the Schrodinger equation. The time evolution of this state vector is given by this unitary operator, which is U, which tells you how the system evolves from an initial state t0 to a later state at time t. So this is the temporal evolution of a state. And you have now answered the fundamental question. How do you describe the state of a system? It is described by a vector in the Hilbert space. How does it evolve with time? The time evolution is given over here. It is this unitary operator which governs the time evolution, and the state vector now satisfies the temporal evolution given by this rate equation, which is what we call as a Schrodinger equation. So now we ask, what should be the properties of this unitary operator? And I will not apologize for using mathematics, because that is the only way you can describe nature. So when you make certain demands on this unitary operator, you demand that, okay, if you carry out successive time evolutions, then they must add up to the total evolution over that interval. So these are reasonable demands to be made. And when you make some such demands, it turns out that these demands can be satisfied if and only if the unitary time evolution operator is described by this 1 minus I omega delta t, where omega must be a Hermitian operator, it must be a self-adjoint operator, and using some dimensional analysis and other things, you can find that it is given by Hamiltonian divided by the rationalized Planck's constant or Dirac constant, or the PEB constant divided by 2 pi. So these are automatic consequences of our stipulation about how a state vector must be used to describe the state of a system. Now, we need not worry about getting into mathematics, because we are certainly, as physicists, interested in trying to understand how nature manifests herself. And when we develop this algebra further, we will be able to connect it to our observations, which is what physics is about. Physics is about observations. It is not primarily about the vector spaces. It is not primarily about mathematics. It is primarily about understanding our observations. You look at the sodium vapor lamp and you see yellow light. And you want to understand this yellow light. And this can be described only in terms of this mathematical machinery that we are now developing. So that's quantum mechanics. So this is the time evolution operator for an infinitesimal time interval delta t. And when you do it for a finite time from an initial time ti to tf, then you must divide this time interval by n times and let n go to infinity, and you find the exponential operator popping out of it as a series summation. So it's very straightforward. There is some mathematics, but it is not beyond what you learned in your high school. So be comfortable with it. And you have this unitary time evolution operator. Notice that I square root of -1 has already entered our discussion. And this is what makes a complex number. And that is the complexity that I'm going to talk about, the complexity of quantum mechanics with special reference to the wave functions being complex. So that's what we are getting into. And now, when you have this exponential operator for a stationary state, you have the eigenvalues E, which is the eigenvalue of the Schrodinger equation, and you essentially have a phase factor over here. So I assume that all of you recognize the phase factor over here. E over h cross has got the dimensions of frequency, that is omega, and you have e to the minus I omega t as the dynamical phase. This is the phase which is called as the dynamical phase, and you have seen this in the Schrodinger equation. When you take the coordinate representation of the state vector, which is what you see over here, you have what we normally call as the wave function. So the state vector is what we began with, and its coordinate representation connects to the de Broglie-Schrodinger formalism wave function over here. So we have not started out really with the wave-particle duality, but we find that it is completely seamlessly incorporated in this formalism, which is quantum mechanics. So this is the dynamical phase, and you already see that the phase means you have essentially a complex number, e to the I theta or minus I theta has got a real part and an imaginary part. But the imaginary part is as real as the real one. It is a plus ib, and a and b are real numbers. However, you cannot build quantum mechanics using two real Hilbert spaces. You need a complex Hilbert space. And that is something which we are going to be using. And I will begin this discussion with the same beautiful experiment which Professor Ajay Ghatak talked about day before yesterday. He gave a brilliant talk on the interpretation of the Young's double slit experiment. And here you see in this picture Niels Bohr explaining the Young's double slit experiment. The quotation is what Professor Ajay Ghatak also recalled, which is from Feynman, that we choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. And in reality, it contains the only mystery. So this is really amazing. These experiments have been carried out, as was also pointed out by Professor Ajay Ghatak. And I will begin with a discussion with the Young's double slit experiment, but with a twist. जैसा कहते हैं ना, कहानी में twist है. So we will do the Young's double slit experiment. If you have sand poured on two slits, you expect two heaps. But if you do this experiment with an electron gun, and I will not discuss this result because Professor Ghatak described it so beautifully in his talk day before yesterday, you get alternate dark and bright fringes. Now comes the twist. I'm curious. I understand that I can explain this experiment only by considering superposition. But my curiosity is I really want to know if the electron went through slit 1 or slit 2. So I decide to spy on this. Okay, I want to find out. And I can certainly do it in a variety of ways. I can just shut one slit. Then I know that the electron would have gone only from the other one. But I keep both the slits open, but I shine light on it. And then I look at the scattered light. And when I look at the scattered light, if it comes from the upper ray, I know it has come from the left slit. And if it comes from the lower ray, it comes from the right slit. So I can spy and I can find out. Now, this is called as a which-way double slit experiment. This is a which-way double slit experiment. And if you do this which-way double slit experiment, this is the kahani mein twist. the interference fringes disappear. So now both the slits are open. You have not done a which way experiment. You see the fringes, but now you do a which way experiment and the fringes disappear. Now this is spooky. Just by changing how you have set up the apparatus, you impact the result of the apparatus. Now you make it spookier. You put a lens here, which will combine the two rays and bring them to a focus. So whatever information you had got is now destroyed because you cannot anymore separate between the upper ray and the lower ray. And the which way information is lost. This is called as a quantum eraser. And when you erase the which way information, the fringes reappear. This is amazing. It becomes spookier and spookier and spookier. Now, this is how nature manifests herself. So let us do this. Let's try to be smart. Let's not put this lens over here. Let's put it very far away, what we can call as outside the apparatus. So let me show it in the next figure. I now have a lens which is very far. It can be like the whole setup experiment is being done in your laboratory. You have got your experimental bench of about 1 meter or 2 meters. But now I put that lens 20 meters away or even 20 kilometers away, or I can even put it in a different galaxy. But I have that lens, which is going to combine the upper ray and the lower ray. And if I make that provision, the which way information is lost and the fringes reappear. So this is amazing. It becomes spookier and spookier. And this was Einstein's worry and the reason for the famous Bohr-Einstein debate. And this whole Young's double slit experiment, it is such an intriguing quantum mystery that it has challenged some of the best minds in the world. Now, let us add a further twist. So this is the twister which I will introduce in this apparatus in the Young's double slit experiment. I'm going to introduce a solenoid, and there is a current which is passing through this solenoid, which can be passed through this solenoid. And this solenoid, I will keep over here in the Young's double slit experiment behind this intermediate space between the two slits. So that is where I'm going to keep that solenoid. And you will see the top section of the solenoid in the next figure. So can you see this top figure? So this is the cross section of the top of the solenoid. And now I do know that when the electrons come, they will have to pass either through slit 1 or slit 2. I have labeled these slits as sigma and xi. And the electrons can only go around the solenoid. But if there is a current flowing through the solenoid, the interference pattern shifts, as you see in this figure. Okay, you have an interference pattern, but if you switch on the current, the interference pattern actually shifts. Now, this is what I call as a kahani mein twister. Okay, because you know that the magnetic field is essentially inside the solenoid. Now, this is the basic electromagnetic theory. Anybody who has taken a first course in electromagnetic theory knows that the electromagnetic field is essentially inside the solenoid. The electrons cannot interact with the magnetic field because the electrons are going around the solenoid, and they have no way of interacting with the magnetic field, which is confined essentially inside the solenoid. But now you have a miraculous result that the fringes shift. Now, this is ghostly. This is spooky, spookier. I don't know how to say that. And this is the Aharonov Bohm effect. And we are going to discuss the Aharonov-Bohm effect using the third formalism of quantum mechanics, which is the path integral formalism of quantum mechanics, which was developed by Richard Feynman. And this is based on the principle of variation, the principle of least action. This is based on a fundamental principle in physics. Feynman was introduced to this principle when he was in his high school by his teacher, and he went on to develop this formalism, which is a fascinating formalism. It turns out that it is completely equivalent to matrix mechanics of Heisenberg, Born, and Jordan. It is completely equivalent to the wave mechanics of de Broglie Schrödinger, but it is completely independent of these two. So here, this is the path integral approach to quantum mechanics, and Feynman developed it based, he was inspired by an idea. The original idea is due to Dirac. Feynman is everybody's hero, and Dirac was Feynman's hero. So Dirac was an outstanding physicist, one of the best minds, and many regard him as the only equivalent of Einstein of his century. Although there are big names that anybody can recite another 50 good names over here. But inspired by Dirac's idea, Feynman developed the path integral approach. And like everything else, this approach also begins with an ansatz. And notice that action appears in this ansatz. Ansatz is like an assumption, like a postulate. It's something that you begin with. You do not derive it from anything. You can only verify it. You can test it. You can conduct 1,000 different experiments and challenge it. And if the ansatz is not, if you don't see anything in your experiment which is in contradiction with the ansatz, then the ansatz holds as a platform to build your theory. So wave mechanics stands on its own ansatz, matrix mechanics on its own ansatz, and this is Feynman's ansatz, in which he talks about a propagator, that the probability amplitude that a particle would go from a position x0 at time t0 to another position x prime at a later time t prime is given by this integral, in which this action is essentially the same as you're familiar with from classical physics. There is a phase factor, e to the I theta. This is action in units of h cross. So notice that the quantum has entered this in a very smart way. And there is a certain amplitude factor, but essentially there is a phase factor which controls the net probability amplitude. Now, this integral is essentially the limit of a sum. And you can sum discrete pieces, but you can have 10 different discrete pieces. So you can have 2 slits, you can have 3 slits, or you can have many more. And you must consider all of these alternative paths, sum over them, and when you consider all of them, you carry out an integration, which is what you see in this ansatz. And it doesn't matter that it doesn't connect with your observables at this stage, because we have only made the ansatz. We have to develop an algebraic formalism based on this, and then we will find certain terms which we can connect to our observations, like the intensities of spectra or what have you. All your physical observations will be interpreted in terms of mathematical consequences of this ansatz. So now we consider alternative paths. And these are complicated paths. I've shown them in different colors, and you can see that I have considered these alternative paths to be scattered by these red and blue bricks, which are somewhere else, and they could be anywhere else in the universe. So one could be on Mars, the other can be in another galaxy. It doesn't matter, because we are not talking about the actual distances. We are only talking about different paths. And all of these paths must be sum over. So this is called a sum over all histories or sum over all paths. And all of these must be taken into account. And you can certainly ask a question that the distance from the source, which is that yellow light, yellow star-like object, which is the source of your particles on the left, and your detector is the screen, which is on the right side, and the distance between the source and the screen is either a few centimeters or a maximum of a couple of meters. It is an experiment you're doing in your lab. And how much time can light take to go to the screen from where it started? And now you're talking about paths which go around Mars or galaxies which are millions of light years away. But then remember that if you're talking about paths, you no longer talk about the momentum. If you know the position, you know nothing about the momentum, and that is no longer a relevant question. So the speeds become irrelevant. That is not even a question that enters our analysis. And I would like to quote Niels Bohr over here, that quantum mechanics does not answer all questions. It tells you what are the right questions to ask. So if you happen to know the path, you have no business to ask about what was the speed of the particle and how could it go to a M87 galaxy and come back, which is millions of light years away. That's not even a relevant question. So this is the power of mathematics. It is unreasonable. And Wigner has this classic paper whose title is The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And what Wigner says in this paper is, the miracle of appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. We can, however, use it. And that's what physics is about. That is what science is about. And that is what technology is about. So it is not for us to worry about whether an electron is a wave or a particle, because we are forcing ourselves to describe nature in terms of vocabulary that we are familiar with, objects that we are familiar with, and nature is not obliged to present herself in these terms. We have to find the best tools, the most effective vocabulary. It happens to be mathematics, no matter how unreasonable it is, which is why I will make no apology about using mathematics. People say that one should not use mathematical equations in a seminar, but I'm not going to follow this recommendation at all, because it is just not possible to do that. So here is our basic ansatz of the Feynman path integral, that the basic kernel is the core, the basic core of this formalism. The basic ansatz is that the probability amplitude for a system to evolve from x0 to t0 to xftf is given by this integral, which involves the phase factor in units of h cross, which is action. Now, this is a shorthand notation, and I will certainly avoid mathematics to a large extent, as you would like me to, but I am not able to do that completely, and I don't consider myself obliged to be required to do it totally. So I will only make an attempt to make minimal use of mathematics, but not avoid it totally. So this is our ansatz, and we will be using this ansatz in which action appears, and the quantum of action, which is there in units of h cross, of course, plays the dominant role. So this diagram tells you that the ansatz involves this phase. Okay, you have this phase, e to the I theta. Okay, theta is the phase angle, cosine theta plus I sine theta. Okay, that's your complex number. And this theta is the phase, and you can represent the phase on a two-dimensional plane, either by Cartesian coordinates like x and y. Okay, you have got two real numbers, you're dealing with two real numbers, x and y, and you write a complex number as x plus iy, but you can also write it as in polar coordinates as rho e to the I theta, okay, which is rho cosine theta plus I times rho sine theta. So this is the phase which is the central object of our discussion in today's seminar, which is the phase in quantum mechanics. I already talked about the dynamical phase, which is the e to the minus I omega t, which you saw from for the stationary states from the solution of the time evolution equation in quantum mechanics. So you have this phase over here, but what does a phase do to a vector? Essentially, it changes the orientation of this vector in the two-dimensional plane, okay? Depending on the angle, the vector can point in different directions. So all of these vectors, they have got the same length. They all contribute the same amplitude, but their phase angle is different, which is why they are oriented in different directions. And if you consider all of these different directions, they will add up to a net displacement, which is 0. And you may have, when you carry out this path integral approach over different paths, it is possible that the amplitudes which are the same along different paths have different phases, but all of these different phases are such that they contribute a net 0 to the total displacement, as you see in the figure suggested by the red arrows. Then they are there, but make no contribution. The only thing that will make a contribution are the in-phase additions, which are shown by the blue arrows in this figure. And those are the ones which are the classical paths. So classical physics is not totally absurd. It is a great approximation to quantum mechanics. It works in many situations, but not in all. And it works in many situations because what is happening to the quantum paths is that they add with different phases, contributing a net null to the total displacement. So that is the only reason classical physics works. Otherwise, it has no business to work. Position and momentum are just not determinable simultaneously and accurately. So let's get back to this Aharonov-Bohm effect. We have got the solenoid, which is behind the slits, and we are confronted with this strange situation that the electrons go around the solenoid. They cannot sense the magnetic field which is inside the solenoid. That is a well-known result. I don't have to discuss that. And the force on the electrons due to the magnetic field, which is the Lorentz force, which is charge times E plus V cross B, will be 0 because there is no magnetic field in the region from where the electrons are passing. But here again is a big departure from classical physics. Force is an idea which is used in Newtonian physics. As a matter of fact, it is the basic ingredient of the stimulus response theory, which goes into Newton's second law, F equal to dP by dt. So force plays a big role over there, but force plays absolutely no role in the principle of variation. In the principle of variation, force plays absolutely no role. Magnetic field, which comes as a part of an important expression in the force for the Lorentz force, also will not impact. And we often worry about this while discussing electromagnetic theory, because we do electromagnetic theory with the magnetic fields, but we also introduce the potentials. And if you take the derivative of the potentials, you get the fields. If you integrate the fields, you get the potentials. But of course, you have to apply appropriate boundary conditions. That's a matter of small detail. I will not worry about it. But the relationship between between potentials and fields is not just a matter of mathematical differentiation and integration. They are certainly inverse processes. But as we get into quantum mechanics, you must appreciate that the fields do not enter the Hamilton's equation, Hamiltonian. The Hamiltonian includes the momentum, and it is the canonical momentum, which is different from the kinetic momentum for a particle in an electromagnetic field, and it includes the vector potential and not the field. So you have seen this result in classical physics, in classical electrodynamics, that the canonical momentum is not the kinetic momentum. You must add the vector potential within appropriate units. It is in this units which I'm using, it is E over C. But then this is the canonical momentum. And how do I know that this is the canonical momentum? I can set up Hamilton's equations using this. And what it will lead me to is an equation of motion for the charged particle, which will be nothing but the Lorentz force law, which is forces charge times E plus V cross B. So that is completely derivable from this expression. So we know that this is accurate and it is absolutely correct. Now comes the interesting thing. The vector potential is not unique. You can have gauge transformations, A going to A prime, phi going to phi prime, and in both of these expressions, the gauge function chi has appeared, the gradient of chi appears in the vector potential, and the time derivative of the gauge function chi appears in the scalar potential. And using this, if you now set up the Hamiltonian and quantize it, which means that you represent operators instead of the dynamical classical variables, which operate on the operand, which is the vector in the Hilbert space, then your equation of motion, which is the Schrodinger equation, is going to look different because you have different vector potential now. So the vector potential in the absence of a current in the solenoid is obviously different from the vector potential when a current is flowing in the solenoid. So although there is no magnetic field in the area, in the region from which the electrons are going past the solenoid, there is a vector potential. And that is what matters, because that is what is entering the momentum operator. So this is your Hamiltonian. It has got the vector potential, and you must write the Schrodinger equation using this Hamiltonian operator, and you can do it with the vector potential A, but if you change the current, then the vector potential will be A prime, and you must solve a different Schrodinger equation, which is now the one in the yellow background. So they both have the same form, but they're not the same. Because the A and phi in the first Schrodinger equation in the blue background is different from A prime and phi prime in the Schrodinger equation for the yellow background, which also means that the wave function psi in the two is not the same. Psi and psi prime are actually different. And I will not get into showing this mathematics. It is not a very difficult. You can do it as a homework problem. You may take 5 to 10 minutes or maybe 5 to 10 days to do that. I'll let you try that out and enjoy the effort. So here it is. The wave function is not the same. Psi and psi prime are also related by the gauge function, which is chi. It is the same gauge function which appears in the transformation of in the gauge transformations of the vector potential A and the scalar potential phi. So if A and phi go to A prime and phi prime, psi must go to psi prime, and this is the beginning of the understanding of this very strange Young's double slit experiment, not just with a twist, but with a very fascinating twist in which we must employ the laws of electrodynamics in a very careful manner. So this is the Aharonov-Bohm effect, and subsequently Aharonov Anandan also did some work on this. And notice that it talks about the significance of electromagnetic potentials in quantum theory. And once you get into quantum theory, it is the potentials which are far more important than the fields E and B. So here you are. We will now, we have got our basic tools with us, which is the transformation of A and phi to A prime and phi prime, and the transformation of the psi to psi prime, which is the wave function. The gauge function chi appears in all of these transformations. And now I'm referring to a process which is an adiabatic process. Because while what has changed? I am comparing two situations, one in which there was no current in the solenoid, and another one in which there is a current. And I can introduce the current, but I can also switch it off. In other words, I've got a Hamiltonian, H, which depends on a parameter R. So this is the control with which I'm controlling the current in the solenoid. And I can change it in such a way that after a certain elapse of time, the Hamiltonian returns to what it originally was. So I can start the current, change the vector potential. There was none earlier. I introduce it, then I take it off, and the Hamiltonian returns. And so there is an external parameter, which is what I have labeled as R. And let us now consider these adiabatic changes in the Hamiltonian. So whenever you have got a Hamiltonian, which can be controlled by certain parameters, externally controlled parameters, such that it can be brought back to its original value, you expect physics to remain the same. You expect the wave function to remain the same. But same means what? Why can it not change in its phase? After all, a wave function multiplied by a complex number represents the same state of a system. So it can certainly change in its phase, and the phase can certainly be changed if you change this externally controlled parameter and bring back the Hamiltonian to itself. However, this was originally studied in optics by one of our Indian physicists that we should all be proud of, which is Shivaramakrishnan Pancharatnam. He was born in Calcutta, studied at Nagpur, and worked with C.V. Raman. It's very sad that he passed away very young. Pancharatnam did this work in the context of optics, and these are the original ideas. This is Shivaramakrishnan Pancharatnam, who died very young. He was only 35 years old. 1934 he was born and died in 69. But then subsequently this work was done in the context of quantum mechanics by Michael Berry. And this is what has come to be known as Berry phase, but it should actually be called as the Pancharatnam Berry phase rather than as Berry phase, because the first original ideas were developed by Shivaramakrishnan Pancharatnam. So here I will like to remind you of a small problem, which is a solved problem in my book, which is solved problem 2.4. But you would have done it from some other book. And it is a very simple problem. If you have a one-dimensional problem, then it argues that the wave function, apart from certain normalization constant and so on, is just the integral over of the momentum which you see in this expression. It can be very easily solved. It is based on this simple idea that the kinetic energy is just E minus V. But this is approximate because V depends on position, kinetic energy depends on momentum, and you cannot get both of them at the same time. There is no way you can get both of them at the same time. So this is the semi-classical argument. So using the semi-classical argument, but using a little bit of quantum mechanics, the little bit of quantum mechanics is here, that the semi-classical argument is p square over 2m is E minus Vx, even if the potential is changing with position, okay? But now you do not represent P as a classical dynamical variable, but you must treat it as an operator, and we know that it is a derivative operator that comes from the fact that the momentum is the generator of translations in homogeneous space. So the momentum operator must be the gradient operator. As you see in one dimension, it is d by dx by minus h cross d by dx. And now you have this operator. So there is a little bit of quantum mechanics. And now we find the solution to a quantum equation, which is not the Schrodinger equation, but we have this operator for momentum, and we operate by this momentum on an operand, which is a function. And the solution to this differential equation, which is a high school problem, is what we are looking for. With the difference that now our momentum must be the canonical momentum, which is not just the kinetic momentum. It must use the vector potential as well. So now we have this additional phase, which is called as the Pancharatnam Berry phase. It is coming from geometrical factors. It is not coming from dynamics. What is coming from dynamics is this e to the minus I omega t, which is in blue color. So that is the dynamical phase, which I discussed in the first 5-10 minutes of today's seminar. The additional seminar, because of the Hamiltonian going round in a parameter space and returning to its original value, which will allow the wave function to pick up an additional phase, which is called as the geometrical phase or the Berry phase, or more appropriately as the Pancharatnam Berry phase. So the Pancharatnam Berry phase is this e to the minus I gamma t, which is an additional phase which must be picked up, and it is coming from this vector potential. Because your canonical momentum is no longer the kinetic momentum, it includes this phase factor, and you have this integral A dot dr coming from the vector potential. No apologies for using mathematics. How and why it is so effective to describe the laws of nature is what Wigner called as the unreasonable effectiveness of mathematics in describing the laws of nature. It is a gift that we neither deserve nor understand, but we can use it. So that's exactly what we are going to do. So you have this integral A dot dr, which is the same for the two vector potentials. That's very easy to see. A line integral over a closed path is a surface integral of the curl of that vector. This is Stokes' theorem. And if you use this, when you take the surface integral of the curl of A, what is curl of A? Curl of A is the magnetic field. B is curl of A. You get the surface integral of B, which is B dot ds, which is nothing but the flux. Okay, so you have the Berry phase or the geometrical phase in these terms in chi, which is the integral of A dot dr, which is obviously different when you had a current in the solenoid and when you don't. So it is not surprising that by switching on a current in the solenoid, you have created a situation that you have changed the phase. And the phase for the two paths, you have got a path for an electron wave packet which enters the slit sigma, and an electron wave packet which enters the slit xi. These are the two slits in this figure. They are encircling the solenoid from opposite sides, but the vector potential has got a cylindrical symmetry. And because of the cylindrical symmetry, the vector potential is along the path for one and opposite to the path for the other. The difference in path will introduce a difference in phase, and this difference in phase is what generates the interference in this ghostly experiment, which is the Aharonov-Bohm effect. So let's take this exercise to its logical consequence. Okay, this is the geometrical phase. Of course, you have got the constants E over H cross C, so you have to do the mathematics right. And as I mentioned, the line integral, this is just like the Cauchy's theorem or the Stokes theorem. And you have the line integral of the vector potential, which is the surface integral over the open surface for the curl of the vector, which is nothing but the surface integral B dot ds, which is a flux. So now you have the flux contributing to this geometrical phase. The geometrical phase will not depend on the total time. The dynamical phase certainly does. But the process must be adiabatic. And this surface integral being B dot ds, the vector potential having azimuthal symmetry, which is what I am representing using this azimuthal angle phi of the cylindrical polar coordinate system. So I can immediately see that the vector potential is along the unit vector of the cylindrical polar coordinates. So it will always be tangential to the path which the electron is taking around the solenoid. But it will be along the path for one and opposite the path for the other. Okay, because the vector potential is unidirectional with both sides. It has got a spherical symmetry. So now, if you evaluate the geometrical phase, which is nothing but this integral from A dot dr from a certain initial to final, and if the initial is the angle 0, and by the time the electrons go behind the solenoid, they would have crossed an angle of pi, 180 degrees of the cylindrical polar angle. So they would have passed through an angle plus pi in one direction, but minus pi in the other. And you can see that the geometrical phase will be either minus flux by 2 or plus flux by 2. So now, with this understanding, we have to solve the Schrodinger equation with the vector potential with appropriate boundary conditions. Now, this is the differential equation, and we know how to solve differential equations with boundary conditions. So let us do it. Let us write this Schrodinger equation in the cylindrical polar coordinates, and the three-dimensional equation will reduce to a single dimension because of symmetry. Z does not matter. Rho does not matter because you can evaluate this at a fixed distance from the axis of the cylinder. So let's consider a fixed distance rho from the axis of the symmetries, from the cylinder, axis of the cylinder, and you have a one-dimensional equation, differential equation to solve. But what are the boundary conditions? The boundary conditions must be periodic boundary conditions, because everything should be the same for phi equal to 0 and phi equal to 2 pi. So you use periodic boundary conditions, and when you solve it with those boundary conditions, solutions exist only for discrete eigenvalues. So this is like any other bound state problem, that when you have appropriate boundary conditions, solutions exist only for certain energies, and this is the solution. This is again a differential equation that you can solve possibly in 5 minutes or 5 days, but no more than 5 days. Just cannot take more than that. Notice that if flux phi is 0, if the flux phi is 0, the solutions for plus integer and minus integer have got the same eigenvalues, which means that you have a degeneracy. Now, this should surprise you, because one-dimensional bound state problems do not have any degeneracy. There is a fundamental theorem which you can learn from Landau and Lifshitz's book, or from my book, if you wish, that you cannot have degeneracy in one-dimensional problems in the case of discrete solutions. But here, the boundary conditions are different. Like in hydrogen atom, the boundary conditions are different for the bound states. The wave function goes to 0 in the asymptotic region. Here it is not going to 0. It returns to whatever value it had when phi goes to phi plus 2 pi. So as a result of this, you have degeneracy. So this is one point, one interesting point that you must note. The second point that you must note, and this is really interesting for us to understand the fringes in the Aharonov-Bohm effect. What if the value of E phi over 2c pi h cross, you see the term in the eigenvalue? If E phi over 2c pi h cross is an integer, then the eigenvalue spectrum is essentially the same because you're just taking the square of one integer or some other integer. It doesn't matter, but you're going to let n take all values anyway, all the way from minus infinity to plus infinity. So the eigenvalue spectrum is essentially the same, which is really very interesting. Now we have everything that we need to understand the mysterious Aharonov-Bohm effect, that when you start a current in the solenoid, the fringes shift. So here you have the Pancharatnam Berry phase. It is coming from the difference in the geometrical phase picked by the two paths, because one is along the vector potential, the other is opposite to the vector potential. So the Aharonov-Bohm effect is essentially an illustration of the geometrical phase, or what we call as the Berry phase or the Pancharatnam Berry phase. This effect, of course, is ascribed to Aharonov and Bohm, but even earlier it was predicted by Ehrenberg and Side, and sometimes it is fully called as Ehrenberg-Side Aharonov-Bohm effect. There's a very nice paper in Nature just a few years ago in 2019, but it's still 5 years now, in which they discuss the geometrical phase from Aharonov-Bohm to Pancharatnam Berry and beyond. Is anybody asking a question? Yeah. So this experiment has actually been performed long back by Chambers. Very, very interesting experiment to do. And perhaps some of you can actually do this experiment and try it out. So here is a simulation of this experiment, which I'm presenting here to appreciate the consequences of this. And in this simulation, you change the current in the solenoid. In the first column, I've got various values that the current can take. This is the magnetic field in the solenoid, which you know this formula from your high school physics or undergraduate physics. This is the flux. And then you determine the vector potential. And then you can determine the geometrical phase, which we just obtained in the previous slide. And you can see that as you change the current, as you change the vector potential, you change the Berry phase, and you can change it to 0, pi by 2, pi, 3 pi by 2, 2 pi, and depending on the phase difference, you will get either constructive interference or destructive interference. And this is how you can move the fringes. So here are some results of this simulation. So when the phase difference is 0, there are two calculations, one with a vector potential 0 and the other with a variable vector potential. The variable vector potential is shown in the gray thick line and the 0 potential by the sharp line. And they are on top of each other because the value of the variable vector potential in the first left side of the figure is 0. So it's the same, they are superposed on each other. But in the right panel, I show the gamma to be pi by 2. And now you see that the fringes shift and they will cancel each other. And you will see why the fringe pattern really changes because of this. And these simulations have been carried out by some of my students, Shubham Ghosh, Uday Kumar, and Harish. We did this work in collaboration with Arvind at IIT Madras. This is reported in the Physics Educator. You can get the details in this paper, or it is also described in my book, in which we have presented this case, but also some of the other cases. So this is, in a sense, the explanation of the Aharonov-Bohm effect, and it is coming from the complex wave function. It is coming from the phase of the wave function, and this is not the dynamical phase. This is the geometrical phase, which one often does not meet in some of the introductory discussions on quantum mechanics. But I will also, in the last few minutes, I would like to tell you about gravitational Aharonov-Bohm effect. We talked about the electromagnetic Aharonov-Bohm effect. So I will first tell you about neutron interferometry. So we are doing a Young's double slit experiment. Basically, you are combining electrons coming from two alternative paths. So I will now combine a neutron beam coming from two alternative paths in this experiment. One is the upper path. So I've got a neutron beam. I've got crystals, and neutrons undergo diffraction in crystals. But this path is modulated by a magnetic field, and I can change the path difference by changing the magnetic field over here, just the way I could modulate the phase difference in the electromagnetic Aharonov-Bohm effect. So here, the magnetic field will introduce a path difference, and when I recombine these two paths by using two additional silicon crystals, one, the intermediate one, which will scatter them back to be recombined on the third crystal, and I see the two beams on two detectors, which are on the right side, DS1 and DS2, in which I do the counting. And from the difference in the counting, I will get either interference which is constructive or destructive. And I look at the interference experiment through this neutron diffraction interferometry. Now, what is interesting is that the neutron has got a spin half, and there is a magnetic moment associated with this. The symmetry group is SU2, and it really takes a rotation through 4 pi to come back to unity for spin half particles. You have studied this in the context of electrons, but it is also true for neutrons, which is also a spin half particle. And from this neutron interferometry experiment, you can actually see the physical manifestation of this 4 pi rotation, which is required for the unit operator. The unit operator you expect from classical physics to be obtained when you rotate things through 2 pi. You just turn around yourself through 2 pi and you see the world to be the same. But if you were an electron, if you are a spin half particle, you will need two rotations, one about your mom and the other about your dad. And, and you need 4 pi rotations. And you can see a confirmation of this result in this neutron interferometry experiment. So this experiment we are now going to do in a gravitational field. So I've got the same paths, AC, CE, AD, and DE. These are the path 4 segments, which I lay in 2 different planes. So on the right side figure, I have ACED in a horizontal plane, but then I can lift the path CE up so that now neutrons going along the path C prime E prime are in a different gravitational field than the gravitational field experienced by neutrons in the plane of the dashed line CE. It's very small, but detectable. And you can do these experiments. The technology is so beautiful. It is so sharp, so sensitive that you can see these variations. Same thing with time measurements. If you have an atomic clock, you keep it on the desk and you raise the clock through just 2 centimeters, it will sense the gravitational field and show a time dilation. So technology is superb and wonderful to have young audience over here in this hall, and also who have joined virtually for this talk. So many of you will be able to contribute to this very exciting field of quantum mechanics and quantum technology. So some of these I have discussed in further details in my book. Also, you're welcome to look at the details. But that reminds me of something that you have heard time and again, that a cat has got 9 lives. Why does it have 9 lives? Because no matter how you drop it, it flips and manages to fall comfortably and safely on its toes. Now, don't do this experiment. Don't toss a cat, although I know that people have done this experiment. Okay. And the cats have survived. I have not heard about any cat which died. How does the cat turn? How does the cat turn? Are you applying any torque on it? Okay, so here is a change, but there is no change. Okay, it is like the Pancharatnam berry phase. You are changing a Hamiltonian and you bring it back to its original condition, okay, adiabatically. And what you're seeing over here is a classical analog of the Pancharatnam berry phase. This is the same phenomenon. I will give you another example in classical physics, which is the Foucault pendulum. And if you have a pendulum which you are holding in your hands at the North Pole, and the Earth is rotating under your feet, it is directly rotating under your feet, the pendulum will oscillate in a single plane. But if you hold this pendulum anywhere else on the Earth, not at the North Pole, not at the pole, but somewhere else, at a latitude of 45 degrees, if you like, or at Paris, where the first experiment was done by Foucault, then the plane of oscillation would turn. And this is one of the most beautiful experiments, as Professor Ghatak also mentioned the other day. And this is again an example of a parameter which is changed externally, and you can account for the plane of oscillation turning using dynamics, but then you have to introduce pseudo forces, which is the Coriolis force. But you can explain it without using dynamics. So don't use the magnetic field B, but use the vector potential A. Okay, so don't use the dynamics, but use the geometrical phase, which is coming over here. And using the geometrical phase, which is not the Berry phase, but it is the classical analog of the Berry phase. It is known, it is also an angle, it is called as the Hannay angle. And I think Hannay discovered this after Berry, because he thought that there must be a classical analog of this. And this is the classical analog of the Pancharatnam Berry phase, or the geometrical phase. And there are these classical analogs. So we have essentially, this is my last slide, in which I hope you enjoyed celebrating the World Quantum Day, the April 14th, as it were, being celebrated day after tomorrow now. This is a week-long celebration. And we have had brilliant talks in the last few days. And we understand the Aharonov-Bohm effect as to why the fringes shift. But let me tell you something else about April 14. You have 4.14 as the World Quantum Day, but Michael Berry was born on the Pi Day, which is March 14th, because the pi is 3.14 or nearly so. And Michael Berry was born on March 14th, the Pi Day. Albert Einstein was also born on March 14th on the Pi Day. So you can play with these numbers. So thank you very much. If there are any questions, I will be happy to take. Neetu, thank you.
Thank you so much, sir. Was so interesting
Thank you,
to
sir.
talk.
Thank you, sir, for your invaluable words, which have enriched our understanding and ignited our passion for quantum sciences. But before moving ahead, there are few questions from our curious learners, which needs your expertise, sir. So, first question is from Mr. Vinayak Singh. He says, what happens if we change the direction of current? Do the fringes appear on the other side than seen from here?
I'm not sure I've understood the question. Can you repeat the question, please?
So I repeat, he says that what happens if we change the direction of current?
Yeah,
Do
of
the
course.
fringes?
Yeah, the vector potential will change its sign, and the whole algebra will respond to that. So fair enough, but the ultimate result will be the same, except that it will be on the opposite side. So the fringes will move in one direction or the opposite side, but the physics doesn't change by changing the sign of the current. Physics remains the same. Details, minor details will change. So no big deal about it. Any other question?
And what role does the size of solenoid plays?
What role does?
The size of solenoid plays.
Also, means if you even the figure which is there on the screen now can tell you that the solenoid has to be of a reasonable size. The geometry has to be appropriate for the conduct of the experiment. The principle of the experiment does not depend on the size of the solenoid, but the details of the experiment means even if you have two slits which are very far away from each other, you will have the same kind of situation. So to the same extent that the size of a slit or the distance between the slits are important in a Young's double slit experiment, these are minor details. They do not change the physics of the experiment.
Okay, sir. The other question is, sir, what happens if we have three slits and then we place two springs at each side and have an opposite current flow on both of them? Does the effect of opposite current nullify the obtained pattern?
It can. In principle, it can. It will need some skill to achieve that. Good luck.
Okay, sir. Thank you very much, sir. There is another question from Deepika. She says that, sir, may you please let me know what is the significance of any field?
Any field?
Yes, sir.
It's a good question. Field, the first introduction of fields, I think, appears in the theory of Maxwell. Earlier works in which fields always existed. Gravitational field existed even before Newton was born and even before his grandfather was born. The gravitational field was always there. But the mathematical idea of a field as having an effect at a distance, okay? Because when you talk about something influencing something else, the common sense, intuitive understanding of man a few hundred years ago was only when the two sort of touched or pushed or pulled each other. The contact seemed necessary. And even when gravity was discussed and even explained by Newton, the mathematical idea of a gravitational field as we understand it today was not introduced by Newton. It was, he used the idea of force being as the cause of acceleration, F equal to dp by dt, but he did not use the idea of a field. It was not used in Lagrangian mechanics nor in Hamilton's mechanics. It gets used only much later in Maxwell's theory. But subsequently, it becomes a cornerstone of physics. And today, even particles are considered as excitations of fields in a certain sense, which is what explains why all electrons have got the same properties, because they are all excitations of the same field. So field is a very abstract mathematical idea. It manifests itself from how the experiments are carried out, and those details are very intricate. The fields of electrodynamics and gravitational fields are understood to some extent. The field for the weak interaction is also understood. In fact, it is understood to be homogenized with the electromagnetic field in the work of Salam, Weinberg, and Glashow. So there is this electroweak unification of these three fields, but a quantum mechanical description involving gravity, of course, is not yet developed. So field is a very fascinating idea, begins with Maxwell and continues to be explored.
Yes, sir. Thank you, sir. There is another question from Suresh Kumar. He says that can the double slit experiment be performed with antiparticles like positrons?
I'm sure it can be. I must confess that I do not know if it has been performed with positrons, but I'm sure it can be. I don't see any reason why the result will be any different. The Young's double slit experiment certainly has been done not just with electrons, but with many things, including fullerenes, fairly large objects. Now, fullerenes are buckyballs, C60. There are 60 carbon atoms. Now, you're no longer talking about a single electron. 60 carbon atoms. Each carbon atom has got 6 electrons. 60 carbon atoms will have 360 electrons. So it is no longer a small system. It is a fairly large macroscopic kind of system. And the Young's double slit experiment certainly has been done with the buckyballs or the fullerenes, and not just with this, but with many other things. But in a more general way, the Young's double slit experiment represents superposition. And superposition is something that you see in everything in nature. So you don't have to go to a Young's double slit experiment to explore superposition. Everything that you see in nature requires superposition. And when you carry out a measurement, you induce the collapse of the state in an eigenstate, which is what you see as a result of the measurement. This becomes interesting when you have two cats in a state of superposition, and if they are in an entangled state, then they are in a Bell state, and that is what leads you to the physics of quantum computing. So which is what I am sure many of you are interested in, but that's a much larger question. But it is all based on superposition. And as Feynman said, this is where the heart of quantum mechanics resides. And it is there in everything. So it is going to be there even in the qubit operations that you will be carrying out. Thank you.
Okay, sir. So another question says that why the diffractive phase acting as an envelope to interfere fringes does not appear in the simulation? I repeat that why the diffractive phase acting as an envelope to the interference fringe does not appear in the simulation?
Oh, this is a simple simulation. You can do this simulation with wave packets also. So this is, you can do it in many different ways. A wave packet is essentially itself a superposition of a large number of harmonics. So that is a Fourier synthesis. So you can do this with wave packets as well.
Okay, sir.
The purpose of this simulation is not to simulate the wave packet, but to simulate the interference. Any other question?
There is another question, sir. Do you find any relative probability for great Heisenberg uncertainty principle to be certain?
To be?
Certain.
अरे ये तो मैं गारंटी के साथ कह सकता हूँ और गारंटी की गारंटी भी दे सकता हूँ Heisenberg principle of uncertainty, you can get into certain squeezed states and so on, but you do not violate laws of nature. Okay, laws of nature cannot be violated by anything which is a part of nature. And we are parts of nature. I don't see any mechanism in which you can get certainty about anything. You can certainly get a precise result of a measurement of position. But when you get that, you will lose information about the momentum and vice versa. So getting accurate information about one or the other is not ruled out. You can get one value with certainty, but then with total certainty, you will lose information about the other completely. Any other question?
So although there are flood of questions, there are questions and questions, but I guess due to shortage of time, I guess we can answer them in the chat box later on also.
Sure.
So let me thank you formally. So thank you, sir, for fostering an interactive environment where questions were encouraged and discussion flourished. Your expertise and wisdom have left an enduring impression on our minds, inspiring us to delve deeper into the complexities of quantum realm. We are truly privileged to have benefited from your profound knowledge and guidance. Thank you, Professor P.C. Deshmukh, sir, for your enlightening discourse and for being a beacon of inspiration in our journey through the National Quantum Week titled Alice in Quantum Land. So thank you very much. Thank you, everyone, for joining us. Thanks a lot. Thank you, sir.
May God excuse you also for all the exaggerations. Not just
No,
me
no,
too.
no, sir. No,
Thank
no,
you very
sir.
much. I enjoyed the IAPT forum very much. The forum of the physics teachers is very dear to my heart. I have been a life member of IAPT for decades, and I absolutely enjoy being over here. Thank you very much. Professor Ahluwalia ji is there. Thank you very
Yes.
much, Professor Ahluwalia, for the
Thank
opportunity
you.
to be here.
Thank you, sir. I just want to say something. May I, sir?
Yes, of course.
Let's see, the success of this exposition lies in the fact that the audience really stuck to this lecture. They remained stuck to this lecture. And I think the interest was shown by the number of questions which were landing in the chat box. I think forum like IAPT has a lot of scope to really pick up such themes from time to time and expose students to these ideas which are just missed in the classroom. People don't even reach that kind of a stage where they can appreciate these subtleties which are there in the kind of subject.
कहानी पढ़ते हैं कहानी में ट्विस्ट नहीं पढ़ते हैं
So दूसरा ये है सर, जब आपकी जो किताब है वो भी मेरे को लगता है एक क्लासिक किताब होने वाली है हमारे हिंदुस्तान में और बाहर भी. तो हमारे पास दो ऐसे महान विभूतियां हैं इस वक्त बैठी हुई इस लेक्चर में. प्रोफेसर घटक, उनकी किताब को पढ़कर कई जनरेशंस ने क्वांटम मैकेनिक्स सीखी. And your book has brought a new touch to that because it's very rare that you will find that right in the second chapter of the book, you start talking about a formulation which normally people don't think of talking about. That is path integral formulation. And I think hats off to, despite the fact that you were talking of apologies about mathematics which you were using, it was reminding me of Hardy's apology of a mathematician also.
Yes.
So that was just wonderful. And there Hardy had said that even when mathematics, which we are doing, has no obvious utility outside, but it has its own beauty when we do mathematics itself. So, but when mathematics goes in the hands of a master like you, sir, it becomes a pleasure. And thank you very much for such a wonderful set of lectures. And Neetu, congratulations for taking this, you know, I would say, challenge to bring this series of lectures to such a level. And I have no other words to say except thank you very much, each of the participants who were there in this lecture, and our worthy speakers, Professor Ajay, Professor Deshmukh, Professor Arvind, whom we have really enjoyed very much in this series. And I am sure that we will keep this kind of things in our agenda of the IAPT also. So once again, I thank everybody. Thank you very much, sir.
So,
Thank you, Adamwale sir,
Neetu,
for your
may
kind
I
words.
sign off?
And thank you, Deshmukh sir, for your so nice talk, intellectual talk.
Okay, so thank you very much. I'm very grateful for the opportunity, and goodbye for now. Thank you.
Goodbye. Goodbye.